হ্যাঁ দেবদ্যুতি কিছু একটা বলবে?
না স্যার, এটা ভুল করে গিয়েছে।
Okay. So we obtained the Lagrangians for different kinds of fields. The Lagrangians are obtained in a way that when we put that in Euler Lagrange equation, we get the equations of motion. And here is the summary of the summary of the free Lagrangians of different kinds of fields. Okay. This electromagnetic field has this Lagrangian, and we know that if there is a electromagnetic field is not in vacuum, then the electromagnetic field is not free. It is interacting with electric charges of the medium. So charge densities and current densities, which is this J. So when electromagnetic field is not free, then the Lagrangian is modified by this term. This is the interaction term of this electromagnetic Lagrangian. But for free Lagrangians, we drop this term because J mu is 0. Because J mu is rho and J, current and charge density. So when they are 0, then the electromagnetic field is free and that term is not there. Okay, so this is Klein-Gordon Lagrangian. This is Klein-Gordon Lagrangian for complex field. This is Dirac Lagrangian, which can also be written in this form. We showed that. And these are Maxwell's Lagrangian, and equations of motions are this. Okay, and this is the form of the Maxwell's equation in vacuum. Today, we will discuss about the parity transformation of the different kinds of fields. That is, we will investigate how under parity or how under space inversion the free fields transform. So this is the fundamental aspect which we want to investigate now. Parity, which is written by this just symbolically. Parity transformation is this transformation. This coordinate t x goes to t of minus x. So x becomes minus x. That is a discrete jump from x to minus x. That discrete transformation is called parity transformation or space inversion, and we denote it symbolically by x nu going to x nu tilde. X nu tilde corresponds to this point. So difference between x mu and x mu tilde is just that t are same and x's are vector x are opposite in sign. Okay. So what we want to investigate basically under this transformation, how this field phi or this complex field or this psi or this mu in this Maxwell's equation, how these fields transform under this transformation. Okay. We know how these fields transform under Lorentz transformation. We have seen that Klein-Gordon field is a scalar field. Lagrangian should be a scalar always. So this is a scalar. So phi does not transform under Lorentz transformation. It is a scalar. So complex scalar field also is a scalar field. So scalar field does not transform under Lorentz transformation. We know how psi transforms under Lorentz transformation, Dirac spinor, because psi goes to S into psi. S is a 4x4 matrix satisfying certain identity. We have seen that. Similarly, this A mu, which is sitting inside F mu nu, the electromagnetic field, that transforms, that A mu transforms as a, under Lorentz transformation, as a Lorentz vector like this. Okay. Same way as the coordinate transform. So A mu is a 4 vector. So it is a vector. So A mu is a vector field. Psi is a spinor field having specific transformation. So all these are under Lorentz transformation. Now we want to investigate how these fields will transform under parity or charge under this transformation. Now to find out such transformation, so let's find out first what is the transformation of a real scalar field? So a real scalar field has this Lagrangian. Now, to find out how these fundamental free fields or free fields transform under parity, we have to assume, or we have to make an assumption without which we can't proceed, because we have to assume that these Lagrangian, free Lagrangians of these fields are invariant under parity. Okay, we assume that we could have assumed in a different way. So just for so in one way we can assume that Lagrangian, total free Lagrangian is invariant under parity. So yeah, under this transformation, this Lagrangian does not change. Okay, you could have assumed any other transformation, but whatever you want to assume, you have to assume, because this field is unknown here. So accordingly, so whatever you will assume about the parity transformation of the Lagrangian, according to that, your field will transform. Okay, but since free Lagrangians are not observables, or can't be probed, so you have the freedom to assume anything. Okay, now assume anything means you assume that free Lagrangians or free equations of motions are always invariant under parity. This is an assumption. If you have to use this assumption to find out how phi has to transform under this transformation so that this Lagrangian remains invariant under parity. And this assumption does not make any loss of generality, because this is a free Lagrangian. So try to understand this very basic point, that to similar, just at the beginning I was jokingly saying, you can't prove that parallel lines can intersect. It is the same way you can't prove how free Lagrangian will transform, because free Lagrangian is a free Lagrangian and it contains space-time coordinates. It also contains the field phi, which is unknown, whose transformation properties is not known a priori. So first we give some status to this free Lagrangian, transformation status to this free Lagrangian, or transformation property we have to assume for this free Lagrangian, based on which we can make further statements about the nature of phi. Like when you construct Euclidean geometry, you have to make few postulates, 5 postulates. What is that? Parallel lines do not intersect. Sum of angles of a triangle are 180 degree, like those. Okay, so once you make these postulates, then on this basis of these fundamental postulates, you can construct further theorems based on this. And using these postulates and some theorems, you can construct more complicated theorems. In that way, you can develop a structure, but at the core, there must be some assumptions which is beyond your group. Those are definitions. In the same way here, free Lagrangians, which nowhere occur in any experimental observation or in any natural process, free Lagrangian you can't observe. So free Lagrangian is something abstract, and now you add to this abstraction the transformation property under parity. So you attribute to this Lagrangian this very fact that this Lagrangian, all free Lagrangians, not only this Lagrangian, all free Lagrangians stated here, which are whether they're Dirac field or Klein-Gordon field or anything, all these free Lagrangians listed here, all are invariant under vector x goes to vector minus of vector x, t goes to t. So under parity. We assume this for all these Lagrangians. We could have, if we have assumed some other transformation properties, we could have made these assumptions, then our investigation should become accordingly, this field transformation will change. But at the beginning, we have to choose something, and it is always easier for us to choose that Lagrangians are invariant under parity, because you can no way observe a free particle, so this is, you can't test it. Like you can't test whether parallel lines can intersect or not. Similarly, you can't test whether these Lagrangians are invariant under parity or not, because there is no fundamental thing to test. To test whether these Lagrangians are invariant under parity, what you need to know how these fields for phi transforms under parity. But the transformation property of the field is at the very first place is dictated by the transformation property of the Lagrangian. So that we assume that these Lagrangians are invariant under parity. So this is the setup. So whenever we are investigating how a field transform under some particular kind of transformation, we have to, that field is the only thing appearing in the Lagrangian, and other elements in the Lagrangian are space-time coordinates. Okay. Now, when you attribute some new transformation, investigate how the field transform under some new transformation, we have always to assume something, how the Lagrangian responds to that transformation. That assumption you have to dictate. According to that assumption actually will tell you how your phi will transform under that transformation. Is this setup clear? Make this very clear. This is the philosophy of all this transformation. Because you are given with this free Lagrangians, you constructed it from relativity and quantum mechanics in some way, and you have this free Lagrangians which contains the fields whose properties you don't know, whose Lorentz transformation properties you know, and you constructed that Lagrangian in a way that they are Lorentz invariant, and when put in other Lagrange equation, they give you equations of motion. This is up to Lorentz transformation. But other transformations, for example, parity or other transformations which I will discuss later, Church conjugation, time reversal, etc. All these transformations, how these fields phi or psi will transform under that transformation. To know that transformation, we have to make some assumptions. Without any assumption, you can't proceed. Or we are not assumption, we should call it a postulate. So we postulate it at the beginning that Lagrangians are invariant under parity. This basically means a free particle, a free theory of fields, a theory of free fields, you can't distinguish when you flip the sign of the position vector of these positions. Okay, so if you reflect with respect to the origin, so if your vector x becomes minus x, your free theory will not change. This is the underlying principle you are assuming. There is no way to prove it. Okay. You can check it for example, classical scenarios, verify it for classical scenarios like equation of motion for a free particle, d2x dt2 equal to 0. For free particle, you can see that if t remains t and x remains minus x, d2x dt2 will not change sign. Yeah? Will it change sign? Yes. Dt will not change sign, but x will change sign. So it will be minus d2x dt2. But for a free particle, we have 0. So free particle is represented by same equation, classical free particle. Okay, so classical free particles equation of motion will not change under x goes to minus x. Clear? So you can verify that for classical mechanical systems. Similarly, Schrodinger equation, you can Schrodinger equation for a free particle, you can check if you change x to minus x, the Schrodinger equation contains del square term. Okay, so if you change x to minus x, so del square will not change, okay, because it is del 2 del x2. Therefore, but If there is a potential, then you can't say whether the Lagrangian will remain invariant or not, because that depends on the nature of the potential. But so far as free particles are concerned, you can always check for classical mechanical systems or quantum mechanical systems that they respect the space inversion. In that, but here, since you have this unknown phi, whose space transformation you do not know from the very beginning, which you have to find out, so you can assume without any loss of generality that all these Lagrangians are invariant under space inversion. Clear? Is this clear?
Yes, sir.
Now, let us proceed slowly. What is that? Okay, let me choose a different color. So suppose this is the, take this Lagrangian of a real scalar field. Okay. So we want to find out how phi, which is a real scalar field, transforms under this transformation. So to find how phi x transforms under parity, we assume that the free Lagrangian is invariant under parity, or the equation of motion remains the same form under this transformation, which is same as both are same. Lagrangian remains invariant, or equation of motion's form remains invariant, both are same. That means we assume that under x goes to x tilde, which is this. Okay. You know, now we will always use this symbol for this parity transformation. So remember, whenever I use x tilde, you mean xt minus x. So when x goes to x tilde, we assume Lagrangian of x. I wrote it as a function of x because all this field is a function of x. So Lagrangian is calculated at a particular x. So for a given x, L has some value if you think of numerical values. So this L of x, in principle, it should, as a function, it should be written as phi del mu phi. L is a function of that, but just for, since we are dealing with the coordinate transformation, to make it explicit, or to point that this Lagrangian belongs to this frame of reference, this coordinate frame, I wrote x here. So under this transformation, Lx should transform to something which should be equal to L of x prime. So that means Lagrangian remains invariant. So, okay. So Lx remains invariant. This Lp is a notation for this, Lpx. So you can drop this. So Lx should be equal to, Lx transformed should be transformed to Lx, which is this L has the same form, only coordinate is replaced by this. So that means it is invariant under this transformation. Here. Now, so under x mu, under this transformation, parity transformation, I have to find out how phi x transforms. So let's assume this. What the x simple, that phi x goes to phi px. Phi p means parity under transforms. Instead of writing phi prime x prime, I just am symbolically writing by phi px. So this is equal to, since x, I can't write, if this is just phi of x tilde, then phi x has not changed. But I don't know what is that. What only I know, I have assumed that Lx remains untransformed. Depending on using this, we have to find out this phi. But since we are making this coordinate transformation, let us assume, we assume that this transformed field is somehow related to value of the field at x tilde by this relation, where we have to find out this quantity, eta p. I don't know what it is. Okay, so this is an assumption. And if I can find out, this is a trial transformation. If I can find out, if I can put in L and check that this is true, and you can get some values of eta p, then we find out a transformation. Okay, this is how, so this is a trial transformation, you can say like that. Now, if we use this, just a minute, if we use this, so let us find out what is LP. LP is LP is this, the new thing with the transformed. So everything is X with the transformed field. Okay. So LP in place of phi P, you can use this. This is trivial. So this is one thing we calculate LP in terms of this phi px, and I calculate L of x tilde. L is given here. So while calculating LP, I just replace the transform field phi p in this form, keeping everything unchanged. And while calculating this quantity from this Lagrangian, I have to replace all these coordinates by x tilde. So here L of x tilde is, so here del first term is del 0 time. So time will not change. X tilde and x are same time, but when x tilde is equal to minus of vector x. Okay, when space part, this space component becomes negative. So in here, so when I write, first term is this, second term is del I phi, but del of this should be with respect to x tilde nu. X tilde nu is this. So del of minus x. Okay, is it clear? So it should be minus. This derivative is with respect to minus x, and this phi is argument is x tilde. Clear? This square. Now, so this remains same, and this, since this is a square, so delta. So this is, you can think of this is del minus x, but since it is a square, that minus can come forward and squared, its minus will go. So it becomes this. So this minus x will go. So I write plus x here because it is square here. Okay, because of this reason. Because del of minus x is equal to minus del of x. Simple. And since it is a del square, so you square, this minus will go. So this minus sign will go. These are very simple, but you have to be very careful about this signs. Now we have to make this two equal, because we demand that this Lagrangian does not transform under this. So if you make this here, if you make this two equal, so in place here for 5p, I replaced by eta p. This is an option. So if you make this two equal, so LPX, this will imply, simply you can look at these two expressions. So all these things are same. Only thing is that eta p square is 1. Clear? So eta p square is 1. This is very simple. That means eta p is like plus 1 or minus 1. So which is to say, so this basically says that for a real scalar field phi, like this, when you make a parity transformation, t goes to t, x goes to minus x, then phi t will transform in this way. That is the conclusion. Clear? So we define phi t as eta p into, like this here, phi x goes to eta p into phi x tilde. That means here phi of tx should go to eta p is plus minus 1. So it should change under parity transform. When you change your xt tx to t of minus x, this field will become plus of t arguments. In the argument x will change as minus x, or it can be minus of this. So okay, or you can simply write in this way also, if you wish. So this is the transformation of the field. Very simple transformation. It flips sign, or it cannot be not flip sign, but its argument will change. Okay, because you are changing x to x to. Clear? This is very trivial for real scalar field. Is this clear?
Okay, sir.
Okay, so now let's come back to for a complex scalar field. Complex scalar field Lagrangian is this. which is phi star phi, and m square phi star phi. Now we have to find out how this field phi transforms under parity, but we assume that under parity transformation, the Lagrangian remains invariant, which means this. This is the mathematical statement of Lx goes to L of x tilde. So Lagrangian will not change. So same L, the functional form remains same. Okay. At this, and the values are also equal. Okay. The transformed Lagrangian has the same value as the value of the Lagrangian at x tilde. Now again, let phi transforms in this way. Okay. Now here phi is a complex scalar field, therefore phi star will transform like similarly this one. Okay. So in general eta p is complex. Then you see LP, again you calculate these things, you write LP in terms of phi p and Lx tilde in the same way. So when you write LP, you get this thing. Just replace phi p, and in place of phi p, you just replace this two. Okay, just replace this two, and you get this. From phi star p, you will get an eta p star, and from phi p, you will get an eta p. So that eta p star and eta p will give you mod eta p square, and the other terms will be like this. Clear? So this is LP. Similarly, if you calculate this L of x means L at x tilde. So this Dirac Lagrangian, this complex scalar field Lagrangian, where all these derivatives now with respect to x tilde mu. Okay, so I have written it like this. All x becomes x mu in the same form, keeping the same form. So again, you just put back all this. So x mu, x tilde, and x have the same time component, but negative x component. So it becomes negative here. When you open it, explicitly write the summation over mu bar, it will be minus of x minus of x. Okay. And but since there are this minus of x means minus of delta x. So this is derivative with respect to minus of x, but there are, which is equal to minus of derivative with respect to x. So one minus for one term, but there are two such products, product of two terms. Therefore, this extra minus will cancel. So this overall minus sign will remain intact here. Yeah. So you will get this. So if you make this two equal, so you will obviously get eta p square equal mod square equal to 1. Okay. Eta p mod square. So LP, so invariance of Lagrangian demands that eta p mod square equal to 1, which means eta p should be a phase like term, unimodular complex number or phase. Okay. That means under this complex scalar field, under this parity, should transforms in this way. Phi tx goes to e to the power I theta p phi tf minus x. Clear? Because eta p, earlier case, in earlier for real field, it was just plus minus 1. But your complex scalar field, you have an extra freedom of a phase you can add here. Okay, so if you write the Klein-Gordon equation or Klein-Gordon Lagrangian at this point with this field, this Lagrangian, and if you write the Klein-Gordon Lagrangian with this field at this point, both Lagrangian should be equal. Yeah, because from that equality only we derive this transformation relation. So this is how this real scalar field and complex scalar field transforms under space inversion. Yeah, these things are very straightforward or trivial to see for the particular nature of the simplified nature of Klein-Gordon and equations, because Klein-Gordon equations or Klein-Gordon Lagrangian, because time and space appears very straightforward in a double derivative in the equations of motion, or in the Lagrangian also. They are just phi dot square and del mu phi like that. Because of that thing, just it is very easy to see that how this Gordon fields transform under parity. The most important thing is, or this now complications begin to start when you try to find transformation of Dirac field under parity. The question is, the Dirac Lagrangian is this, and here also we assume that under parity, that is under this Dirac Lagrangian, okay, this Dirac Lagrangian remains invariant. That means Lx goes to Lpx or Lx goes to L, same L. Okay, so the transformed Lagrangian should be same as the Lagrangian at point x tilde. Okay. Now just give me a minute. You have to just give me a minute. Break for 1 minute. Hello. Okay. Is this clear up to this point, up to this free and complex scalar fields transformations?
Yes, sir.
Yes, sir.
Okay. Now for Dirac field, we start from the same assumption that Lagrangian remains invariant under space inversion. If you flip the sign of the space coordinates, keeping intact time, the Lagrangian remains invariant. Okay, which means this Lagrangian written at point x mu should be same as this Lagrangian written at point x tilde mu. This is the meaning of this statement. Okay. But when written in terms of Lagrangian, when written in terms of this transform field, this field will also transform. So, okay, in general, we have not said that field will remain invariant. We are determining how field will change with this transformation if Lagrangian remains invariant. Okay, but those changes are not very appreciable if for real and complex scalar field, because only the field forms gets multiplied by plus minus 1 or a phase for real and complex scalar field, but things will be different from now on, because now we are entering the Dirac field, and Dirac field has its own complications and beauties because of this fact that this phi is a structured object, 4x1 object, not a single component object. Now, so Lagrangian remains invariant. So under this space inversion transformation, we assume that phi x goes to phi b. Now the question is, we have to determine what is it. This is just an arbitrary generic representation of the transformation. Now, how it is related to the field at x tilde. So how it is related to this tilde, that means if I know this, then I know how field phi transforms. Okay, so relation between the transform field with the field value at x tilde, that will give you the known transformation. So we assume that now this thing is that since phi here is a 4 cross 1 object, it is a 4 cross 1 object, the transform field should be a 4 cross 1 object. It has to be related to this 4 cross 1 object. Okay, now you can check that like previous case also, I could have written this as a number, as some constant into psi, where there is just a single constant. If I would have written that way, then we would not get any general result, because then we would get same kind of results, because then that is not a general thing. The most general thing would be to assume this unknown constant as a 4 cross 4 matrix, because that is the only general form which makes this as a 4 cross 1 matrix. We could have written it as just a number into a 4 cross 1, that will also make this matrix 4 cross 1, but then the structure of the Dirac equations, Dirac Lagrangian, will not be reflected here, and we will only get a trivial kind of transformation, which is not a general transformation. To get the general transformation, we have to take the most general form of transformation we can think of, and that is the most general transformation means here at least we can say P should be of the order of 4 cross 4. P should be a 4 cross 4 matrix. Okay, so now you calculate this one and this one. So calculating LPX means writing this whole Dirac Lagrangian, just replacing the field by psi p. So this is the same as Lagrangian, nothing as x is x, everything is same. Now here you have to replace psi p to use this equation. Okay, to use this equation, sorry, to use this equation. If you use this here, that means you have, in place of this you have to write p psi, and here you have to write something. So what you have to write here, because you can check if psi p is this, so this is basically psi p dagger gamma 0. Okay, this is the definition of psi bar. So from here you get what is psi dagger. If you take it dagger, so you dagger of this thing, so a b whole dagger becomes b dagger a dagger. Okay, and you multiply it by gamma 0 from right, you will get this, and this is the definition of psi bar p. So in place of this, okay, this is, so this you write as here, where you introduce 2 gamma 0 here, because gamma 0 square is 1. You now know these techniques. Now, and because 1 gamma 0 with this psi dagger will give you this psi. So you will have psi bar p of x will be psi bar x tilde into this thing. Look at these equations and see whether you can, if there is any confusion. If psi p is this, psi bar p should be like this. Okay, using this definitions of psi bar p in terms of psi dagger. Clear? Now you have to use this and this in place of this in this Lagrangian. If you use this LP becomes, in place of this you just replace this psi p x, you replace by psi p bar x, you replace by psi without p thing, but then argument will be x tilde. Okay, this thing. So this thing here, this thing will remain same. Okay, and this thing, this IPX becomes this, and you do some these things, just expand it Now the thing is to note here is that important thing is that here I just did a manipulation where because ultimately I have to make it equal to this, which is x tilde. Now here what I did, I kept it here, same this term exactly here. I change this I to minus I, and that minus is absorbed here in the del in this here minus here, because this is derivative with respect to delta of minus x, because that will come from here. So we have to equate this to, keeping this in mind, we made this change here. So to make this change x to minus x, so this is gradient taken at point x, this is gradient taken at point minus x. And to make this change, we have to compensate it by this minus sign, because this is a plus sign here. Okay, so LP is this. Similarly, we can find LFX bar, which is same as just Dirac equation, just written sorry, Dirac Lagrangian, just written at this coordinate x tilde, and x tilde coordinate means same here. It should be minus x. Okay, this delta mu should be minus x. And now you compare this to, now if you, so what, now look at very carefully. If you compare this and this, equality of these two would imply what? Equality of this expression with this expression, whole expression with whole expression. Okay. Now you check if you have to compare this, because you can only way these two terms can be equal in general, because you have to, this is a time derivative term at the first term contains a time derivative, second term contains a space derivative, third time contains no space time derivatives. So individual terms should be equal. So this will imply, you can check. So these calculations you have to check very thoroughly, and you have to perform your own once you understand it. So keep this. So this would imply what? This would imply P dagger P1. Why 1? Because compare first term of this expression and first term of this expression. What is that? Gamma's. So this psi bar is here, psi x is here. So here also psi x is here in the. So these two are equal. So what is extra? Gamma 0, P dagger, gamma 0 for the first term, I again gamma 0, and here from P will come, but two gamma zeros will give you 1. So gamma 0, P dagger, this is 1, but 1 P again come. So gamma 0, P dagger, P and psi. So here also you have psi gamma 0, so that gamma 0 and gamma 0, and nothing else, but again the delta psi here also. So P dagger P is the bare extra term here, which should be equal to 1 for the first term. So this is 1. So P is a matrix which should satisfy this equation. That means P should be a, what is that called?
Unitary.
Unitary matrix.
Sir, I have a question. Are we assuming that P and gamma 0 commutes?
No. I have not assumed. I can't assume that. P is a 4x4 matrix. Gamma 0 is another 4x4 matrix. I have never used any commutation relation here, because when you multiply it by this, gamma 0, P dagger, gamma 0 into gamma 0, these two gamma 0 will give you 1. Gamma 0 square is 1, so they can be dropped. So the thing which comes after P dagger is this P for the first term. So gamma 0, P dagger, P. I am not changing the positions of this, relative positions of these matrices. Clear?
Okay, I get it.
Similarly, because for you, I request you, all of you, please do it carefully without, so see, once you see through this, but try to do it yourself. Okay, just don't look at these calculations and try to understand. You have to do it yourself, otherwise you can't follow. Similarly, because these are very tricky, I mean, simple, but very, you need very much attention to do these things correctly. Secondly, from the second term contains a derivative with respect to minus x. Okay, space derivative at minus x point. Here it also is there. So this, okay. So what else is there? For the second term, you have this term. This is common. This is common. Again, delta x. I'm sorry, delta x and this, these are common things. So what is extra here? Gamma 0, p dagger gamma 0 minus, here's a relative difference of sign, remember. So gamma 0, p dagger gamma 0 into this gamma vector. Gamma vector means it is a summation over gamma I, gamma 1, delta x, del del x, gamma 2, del del y, gamma 3, del del z, like that. So what we get? Gamma 0, p dagger gamma 0 into vector gamma, I mean this gamma I, into, there is a p here. So you get this, look at this, gamma 0, p dagger gamma 0, this 3 into gamma vector, this gamma vector I wrote by I, gamma I space part, into this p. This should be equal to, for this, from this expression, minus of gamma I, because of this relative sign, and this only gamma the vector is there. Is this clear? Is this clear? Okay. So similarly, for the last term, it is very easy. Last term contains only m psi bar psi. Here only whatever without this m psi bar psi, gamma 0 p gamma 0 into p. So sorry, gamma 0 p dagger gamma 0 into p. Okay. So these three equations, identities, p has to satisfy. While deriving this identity by comparing these two equations, I have never make use of any commutation relation between gamma 0 or p. Okay, because their positions I have never changed. I am not allowed to change that because a priori I do not know what is the commutation relation between p and gamma 0. Okay, so I just use this. So p has to satisfy these three equations, and you can check very easily that P is a 4x1 matrix. So you check. So this is solution I give you. Check that for gamma 0, you can intuitively see gamma 0 is gamma 0 dagger, gamma 0 dagger is gamma 0, so gamma 0 square is 1. So p equal to gamma 0, if p is equal to gamma 0, it satisfies this equation. It satisfies this equation also, because you can see you put p equal to gamma 0 and gamma 0 dagger is equal to gamma 0. Therefore, this equation will become gamma 0, gamma 0, gamma 0. So 3 gamma 0s will make 2 gamma 0s will go. So gamma 0, gamma I, gamma 0 is equal to minus gamma I. That means gamma 0 and gamma I anti-commutes, which is a true relation from Clifford algebra. Okay, so this relation is also satisfied by gamma 0. You can check. And also this relation, because if you put gamma 0, product of 4 gamma 0 should be 1, because gamma 0 square is 1. So this is a trivial solution for this. Clear? Now you can check. You can check that if you put gamma I here, it will not be satisfied.
Yeah? The solution, is the solution unique?
Yes, the solution is unique. Why it is unique, I will come to that a little later, because to prove that I have to show something first that is a unique solution.
Okay.
Okay. Now, but you see that here, at least this is one solution. Clear? So one solution for p is gamma 0, and you can always check. You see that if you multiply this by any constant which is a phase, which will not alter all these properties, because if eta p into gamma 0 is equal to p, if eta p is a phase, then its dagger into p will be same. Okay, so everywhere this dagger and P appear, so the first part will cancel and same relations will be valid. Okay, so in general you can see eta P is a phase and you can write P is this. So you see that how psi Dirac field, which is a complicated 4x1 object, not complicated, which is a different kind of thing. Complicated is a relative word. This field transforms under parity as this eta P gamma 0, which is a 4x1 matrix, into psi x tilde. So this is how the Dirac field at 2 points, at the x point x and at the reflected point x tilde. 2 space-time points. Time part is same, but space part is reflected. How that 2 points are deleted. Okay. Clear? So this is how this Dirac field. So phi transforms in this way. Clear? I will come to this a little later, more detail, because lots of things has to be done with this Dirac field's parity transformation. Then we will see. You can answer Shoptosho's question that whether how to see whether this is unique or not. But okay, so let's come back to this. Go back to this the last field, which is electromagnetic field. Okay, how it transforms under parity. So remember, okay. So how it transforms under parity? So remember this Lagrangian is this, where f mu nu is this. Okay. So I will not discuss it in. So since I have done these calculations, you can check thoroughly, because now this expression I can write like this. Okay. Now there are two terms, minus 1 by 4, this term into whole thing, and minus and minus, this 2 minuses plus 1 by 4, this term into again whole thing. Okay, now you can check that in the second term, if you interchange mu and nu, you are allowed to do that because both are dummy indices. So in the second, without doing anything in the first term, in the second term, if you interchange mu nu, so this part will look like in this way of the same term, and this part will be minus of this. So these two terms will be exactly identical. Therefore, this minus 1 by 4 and minus 1 by 4 will make you minus 1 by 2. So you can write this term. Okay, so in this way you can write it. Now, what we have to do, we have to assume that this Lagrangian L is invariant under Lorentz transform, under parity, even for electromagnetic field. Now, so for this, before doing that, let us write this, opening this mu and nu indices like this. So you can write this expression, that the same L as in this way. You can check that. I'm not expressing it. You write, remember this mu 0. So when mu nu are equal, these terms will give you 0. So only those terms will survive where mu and nu are not equal. And that terms corresponds to mu equal to 0, nu equal to I. And the other terms, mu equal to I, nu equal to 0, and mu, nu, and I and j when I, j are different. Okay. So these three kind of terms, here there is a summation over I, here is a summation over I, here is a summation over I and j. Okay. Like this. Now, the same thing, the assumption here is, under this parity, Lagrangian does not change. Okay, so we have to equate these two. Okay, so again we assume under this parity, under this parity, we see that a mu x, we have to assume some transformation, becomes a mu this x. But this is unlike Dirac field, this is not a 4-component object. This is not a 4x1 matrix. For a given mu, this is a single component object. So like real scalar fields, or complete scalar fields, I relate it to this, I assume this form of this field transformation by introducing a term eta p, which we have to determine from here. Okay. Now, I have not done this. You have to do this. It is your home task, or you can check at home. If you have to make this LP and this Lagrangians are same, invariance of this Lagrangian would imply. So if you have to put for LP, L is this. Okay, so for LP, you have to put all these, replace all these A by P, APs. Okay, all these A's by APs. Okay, and for L equal to X tilde, for this thing here, in this expression, you have to replace all these X by X tilde. That means all the time derivative will not change, only space derivative will change their sign. Okay, so accordingly you have to do, and you have to compare. And you can see that if you do that, I have not shown this, but I have written the answer. If you do that, you can see this would imply strangely two different results. Either this eta p, so these two are the results. So AP 0 and I, they will transform differently. So eta, okay, so either this is plus, so space, sorry, this is time part. So 0th component of AP will not change, space part will flip sign, or 0th component of A will change, space part will not change. Okay, so this invariance of Lagrangian demands that this field A mu can, if this A mu X has to keep this Maxwell's Lagrangian invariant under parity, then under parity it has to transform in this way. It has to transform either as A0 and this is AI, either as minus A, like this way you can write, either as this is this part, or as minus A0 vector A, or as this. Okay, so there are two possibilities, two independent possibilities, both of which can be true, and based on this free theory of free fields, you cannot choose, we can't choose between these two possibilities. You get this point? You can, if you do this calculation if you own, you will see that there are two possible results which can lead you to the equality of the invariance of the Lagrangian in under space inversion. I have not explicitly done this calculation because this is very simple. You can check that. So to summarize up to this point, what we have done, I think it's summary. Oh, yeah. So this is a summary. You can. So free Lagrangians are assumed to be invariant under parity transformation. So this is the starting point. Free Lagrangians, you attribute their transformation property to be invariant under this transformation. When you change this x to x nu, Lagrangian transform, and you exploit this assumption to find out properties of the fields under parity. And you see, we have seen that under this parity transformation, real scalar field transforms like this, okay, just plus minus this. Complex scalar field transforms like this, where eta p is just a phase. It is a special case where eta p is plus 1 and minus 1 because things are real, because then this phase is just plus minus pi. Okay, this is obvious. But for Dirac field under this transformation, the Dirac field will transform in this way, gamma 0 psi, and psi bar accordingly will transform like this, eta p star. Eta p can be a phase, okay, in general, like this. So these transformations will keep Dirac Lagrangian invariant. Okay, so this 4 cross, this is a, remember, this is a 4 cross 4 matrix sitting here. So this is a 4 cross 1 object. This is a 1 cross 4 object, psi bar, And you can check that right hand side also respects this. Okay, so this has been derived in these previous calculations. Okay, similarly, electromagnetic field under parity transforms in this way. So one way is A0, we have to separate it because two component, there are four, it's a four vector. So space part and time part transforms differently. One way of transformation is this. Time part does not transform, space part flips side. And this part is different. Space part, time part transforms flip side, space part does not flip side. So in both, if field transforms in this way or in this way, Lagrangian will remain invariant. Actually, if it is a, since mu is a field, it has to transform in a particular way, but so far as free fields are concerned, you are not allowed to tell which way electromagnetic field should transform just from the free field. You have to see something more. We will see that. But this is how all these free fields transform. Here, this is how all these four kinds of fields transform. You can ask me if you have any queries. Hello.
স্যার হয়তো আপনি বলেছেন কিন্তু আমি হয়তো মিস করেছি যে এই যে ডিসক্রিট ট্রান্সফরমেশন গুলো করছি তার জন্য ল্যাগ্রাঞ্জিয়ানের ইনভেরিয়েন্সটা দেখছি। তো এটা তো ডিসক্রিট ট্রান্সফরমেশন, এটা তো কোনো কনজারভেশন ল দেবে না, কিন্তু আমরা এটা কেন পড়ছি?
হ্যাঁ, সেটা একটু আচ্ছা, কেন পড়ছি, কারণ আমরা when we will look at natures, when we will look at physical processes involving interactions of quarks and leptons, okay, or baryons and mesons, whatever, যখনই কোনো physical interaction আমরা দেখব, we can experimentally determine whether that physical process, which is whether that process is invariant under parity or not. That we can experimentally determine. We can check whether any physical system, whether that is invariant under parity or not, that we can always check. Because like I said, that neutrinos are always found to be left-handed. Okay, so that means right-handed neutrinos are never found in nature. That is an observation. So that is another way of saying that for neutrinos, parity is not conserved. In all interactions involving neutrinos, so whenever you look at the interactions, you will see that if you look at the mirror image of these interactions loosely, then mirror image of these interactions will not exist in nature if they involve neutrinos. And if they involve electrons, they will exist in nature. That means physical processes, you can say for physical processes, you can observe whether it is symmetric or whether it is symmetric under parity transformation or it violates parity. Okay. So if you can check it physically for physical processes, that means ultimately what you have to do to make a theory of this, you have to write down an interaction term in the Lagrangian. Here, when you have to observe any physics, you have to construct a theory of a physical process, field theory of a physical process. Ultimately, you have to write a Lagrangian for that physical process, because in the Lagrangian formulation, say, then for an actual process to write, to make the theory for an actual process, when you have to write the Lagrangian, that Lagrangian will not be just free Klein-Gordon Lagrangian or free Dirac Lagrangian or free Maxwell Lagrangian. That will contain some new terms or some interaction Lagrangian. Okay. Now, that whether from experimentally you can see whether that process respects parity or not. Parity is whether that process is invariant under parity transformation or not, that you can see in nature. Okay. Now, depending on that, you can say that therefore its interaction Lagrangian, which we'll write in theory, that interaction Lagrangian will be parity symmetric or antisymmetric, or they will be invariant under parity or not invariant under parity. If you know that real process, then you can't make any assumption. Just from your observation, you can tell whether the Lagrangian, which describes that process, which cannot be a free Lagrangian, which has to be an interaction Lagrangian, that Lagrangian whether that Lagrangian should be invariant under parity or not, that you can directly say by observing the process, because you are writing the Lagrangian describing the process directly. Now, when ultimately we have to write the interaction Lagrangians for different interactions, say electromagnetic interaction, we have to write the interaction Lagrangian. And we know that electromagnetic interactions conserve parity, or their parity under parity transformation. Electromagnetic processes are, descriptions of electromagnetic processes are not changed if you change x to minus x. Okay, but say for example, if you see a weak interaction, we'll see tell this later. The weak interactions are not so. If you observe a weak interaction, now if you make a parity transformation of this process, then that interaction will not remain same, because this is so that way this parity transformation will differentiate between, this is the basic nature of these electromagnetic or weak interactions, which you can distinguish in terms of parity transformation. Because in nature, you see that and weak interaction, say if you see a weak interaction, if you look at its mirror image, you will see that the image which is looking at its mirror, that does not exist in nature, that does not happen in nature. A process which you are observing in the laboratory, if you look at its mental parity transform process, that means if you think of a process which is same as its mirror image of this process, okay, but you can't see that process in nature, you can see only in that image. That means in that interaction, parity is parity is violated, okay, or that system is not invariant under parity. But whether an electromagnetic interaction, you will see whether if when you are looking at an interaction, its mirrored image, that mirrored image should match with an actually occurring processes in nature. Then we say that, okay, this process is invariant under parity transformation. Okay, so ultimately we have to write down the Lagrangians for the physical processes, because only for this are called the interacting Lagrangians. I will come to that. But these interacting Lagrangians are the most important thing, because they are only related to observable things, cross sections, decay wheels, like that. Free Lagrangians are nothing. They are not related to anything, any observable thing, because free thing you can't observe. Okay, now, so, but these interaction Lagrangians, you can directly tell whether these interaction Lagrangians are invariant under parity or not. Now, when we will try to construct the interaction Lagrangians, we have to construct from the very beginning in such a way, since we know that it will conserve or violate parity from observation. So theoretically, when we want to construct the Lagrangian, from the very beginning, we will construct it in that way to match with the experimental result. If it is a weak interaction Lagrangian, I have to construct it in such a way that the weak interaction Lagrangian violates parity. Now, the interaction Lagrangian should be constructed out of these free fields, because ultimately it is the interaction between the free fields. Now, for that, I have to, at the beginning, first know how free fields transform. Now, how free fields transform under parity, to know that, we just impose this condition that free Lagrangians do not transform under parity. That will not change any experimental situation because free Lagrangians are not involved in experimental situations. Okay, so this is the more or less setup. So this setup will be more and more clear as we proceed. But since you asked this question at the first place, so this is the motivation for studying how free fields transform under parity, assuming free Lagrangians to be invariant. Now, ultimately, we have to look at the real processes involving quarks, leptons, etc., their interactions. We have to construct their Lagrangian. Now, to construct their Lagrangian, we have to write those Lagrangians in terms of the free fields. Now, experimentally, we know whether that interaction Lagrangian should be parity conserving or parity violating. Accordingly, we would construct the Lagrangian in that way. Okay. When there is no theory, other theory. Just looking at the experiment, we have to construct the Lagrangian in such a way that it violates parity or respects parity so far as the experimental observations are concerned. Now, to construct that, we have to use the free fields. For that, we have to know how the free fields transform under parity at the very beginning. That's why we are investigating this.
Okay, sir.
Okay, this is a very elegant plan, and you have to live with it for longer period of time to grasp every details. Okay, I just stated it within 10 minutes or 5 minutes, but as we go on, I will again state this, and as this I will show you this development of this theory, then you will slowly grasp. Okay, but these are very elegant and involved, complicated things, but very beautiful things if you understand. But you understand this, how I get how free fields transform. We are getting how free fields transform under parity. This we are deriving, assuming free Lagrangians to be invariant. Okay. Now this transformation properties we will need to describe real processes, whose real processes parity transformation we already know from experiment. With that in vision, we are finding this out.
Okay, sir.
Actually, বোঝা গেল মানে প্রথম শুনে একটা ধারণা হয়, তারপর আবার শুনলে আরেকবার মানে বোঝা গেল কথাটা is a evolving concept. কিন্তু
আলটিমেটলি শেষে গিয়ে দেখবো হয়তো বুঝলামই না।
আলটিমেটলি আলটিমেটলি বুঝবো না, বোঝার কিছু নেই। দেখো মানে আমি যতটুকু বুঝেছি সেইটুকু তুমি বুঝবে, এইটুকু আমি গ্যারান্টি দিতে পারি, কারণ আমার সেটুকুই কাজ। যতক্ষণ না বুঝছো আমার সেটুকুই কাজ। আমি যেটুকু বুঝেছি সেটুকু তোমাকে আমি বুঝিয়ে দেবো। এখন আমি তো জানি না আমি কি বুঝিনি, সেইটা আমি তোমাকে বোঝাতে পারবো না। আমি বুঝিনি, আমি তো জানি না কি বুঝিনি, কিন্তু আমি যতটুকু বুঝেছি সেটুকু আমি তোমাদের সবাইকে বুঝিয়ে দেবো, যদি আমাকে আমার সাথে কোঅপারেট করো। ওকে,
হ্যাঁ স্যার, ডেফিনেটলি।
তো ঠিক আছে। দেখো মানে এখন কি বলতো, ওই মানে তোমার ওই ডোন্ট লুক অ্যাট দিস কোথায় যেতে হবে, লুক অ্যাট দিস নেক্সট স্টেপ। একবার দেখে নিয়েছো, একবার বলে দিলাম ওখানে যেতে হবে, এইবার ওখানে থাকানোর দরকার নেই, জাস্ট কনসেন্ট্রেট অন দি নেক্সট স্টেপ। সিঁড়ি ওইভাবেই ভাঙতে হয়। নাও ঠিক আছে, এই জায়গাটা আর যদি কিছু প্রশ্ন থাকে কারোর বলে দাও, কারণ আমি ফ্রি ফিল্ডের প্যারিটি ট্রান্সফরমেশন বার করেছি, যেভাবে বার করেছি তাতে যদি কারো কোনো প্রশ্ন থাকে, ক্যালকুলেশনগুলো তোমরা বুঝতে পারবে দেখলে, আমার ধারণা তোমরা যথেষ্ট এক্সপার্ট ক্যালকুলেশনে, বুঝতে পারবে। কিন্তু ফিলোসফিটা কি এখানে এই সামারিতে সব লেখা আছে। এই free Lagrangians are assumed to be invariant. এটা ইউজ করে আমরা এই ল্যাগ্রাঞ্জিয়ান ট্রান্সফরমেশন গুলো বার করেছি, এই ফিল্ডের ট্রান্সফরমেশন গুলো বার করেছি। ঠিক আছে, এখন শুধু এইটুকুই করেছি। কেন করেছি তার উত্তর হচ্ছে কাজে লাগবে বলেই করেছি। Can I proceed? Should I proceed more?
Yes, sir.
এবার look at these things. এবার let me come back to Dirac equations. The Dirac equations, in the Dirac equations you have this gamma matrices which satisfy Clifford algebra, and you know that gamma matrices dagger you can write in this way. So these two independent equations you can use. So gamma mu dagger means, so gamma 0 dagger is gamma 0, gamma gamma I dagger is minus gamma I. Here these two equations say that. Okay, so this is, so I'm just doing some recapitulation of some Dirac equation gamma matrix properties of gamma matrices, and you know trace of gamma matrices is 0. You know this?
Yes, sir.
Okay, can you? Okay. And remember, so now what I am, okay. Now you remember this sigma mu nu is a matrix symbol I used to denote this matrix, which is the matrix which is sitting in this Lorentz transformation matrix S, as this S psi is the matrix Lorentz transformation of this Dirac field, and that S has this form, if you remember, 1 minus I by 4, something like that, sigma mu nu omega mu nu. That sigma mu nu is this matrix. This is just a symbol which is I by 2 commutator of gamma matrices. Okay, not anticommutator. Anticommutator is 2 eta mu nu. This is a, so sigma mu nu itself, for a given mu and given nu, sigma mu nu itself is a matrix. It is not like some mu nu element of some matrix. Sigma mu nu itself is a matrix for a given mu nu, and since it is defined in this way, it is a commutator. You can check that there are 6 independent matrices. This anti-symmetry gives you 6. You know this. I discussed this earlier also. So you can write these 6 independent matrices as this. Okay. So there's all this sigma 1 0 is minus of sigma 0 1 because of this, and sigma 0 0, sigma 1 1, etc. are just 0 matrices. So only 6 matrices are independent, but which in general can be written in this way. Okay. And you know that your gamma 5 has been introduced to you in quantum field theory class. Hello?
Yes, sir.
Yes, sir.
Okay, so gamma 5 is this, you know, and you can write gamma 5 below up, that doesn't matter, that 5 is not like a Lorentz index. And you know that gamma 5 always, use this definition and all these definitions, gamma 5 always anti-commutes with any of these matrices, any 4 gamma matrices. Clear? So these are the 4 basic, 4 important properties of gamma matrices. So this is not a property, this is just a symbol for this notation. This is a definition of gamma 5. So the 1 and 4 are 2 properties of gamma matrices. Now you look at this set. So you consider a set of matrices where this is 1 is identity matrix. Now usually so we work with a dimension where gamma mu is a 4x4 matrix. We know that there is the minimum dimension of gamma matrices, and we stick to this minimum dimension for our simplicity. So this is one is a 4 cross 4 matrix. Now I write 4 gamma matrices. So there are 4 such matrices: gamma 0, gamma 1, gamma mu, sorry, gamma 2, gamma 3, 4 gamma matrices. Now we write sigma mu nu, this matrix, which is basically 6 independent matrices. So basically writing this means the shorthand notation for all these 6 matrices. Instead of writing this 6, I just write single sigma mu nu and it represents 6 matrices. Now I write another matrix gamma 5 into gamma mu, where gamma mu can be 0, 1, 2, 3. So this is basically a set of 4 matrices, which is gamma 5 into gamma 0, gamma 5 into gamma 1, gamma 5 into gamma 2, gamma 5 into gamma 3. Okay. And one last matrix, gamma 5 itself. So in this notation, how many matrices I have written? 16, because 1, 4, here 6, here again 4, here again this is one matrix. So it is a set of 16 matrices, set of 16 definite matrices, gamma matrices. I have not taken any form, but general gamma matrices. All these matrices are constituted out of gamma matrices, because one is identity, of course, constant matrix. All these are constant matrices. One is identity. Gamma mu's are the gamma mu's satisfying this Clifford algebra. The sigma mu nu is the matrix constructed out of gamma mu nu's like this. So, which again in turn satisfies this Clifford algebra. This is gamma 5 into gamma mu. These are again 4 matrices, same gamma mu's. And gamma 5 is again defined in terms of this product of 4 gamma mu's. And also singly gamma 5. So there are a collection of 16 matrices. Is it clear that this represents a collection of 16 matrices?
Yes.
Now, this is a very interesting and very, when I did this exercise in my student days, I got very excited. I mean, I liked it, not excited, I liked it very much. You have to prove that all these 16 matrices are linearly independent. You can prove that. So, in other words, you have to see what you have to prove is an exercise, a beautiful exercise, I think. And if you can do this exercise, have you done this anyway in your QFT
Yes,
course?
sir.
Okay,
Yes.
then, okay. So if you can grasp this beauty of this result, you can check that all these 16 matrices are linearly independent. Okay. If you use them 4 cross 4 matrices, all of them are linearly independent. And so you have proved this, right?
Yes, sir.
Okay. Then for that, you have to need all these trace theorems like that.
Trace properties.
Okay. That means, and if you can check that any other matrix will always be, which is different from this, will always be a linear combination of this. This is the max set of, in 4 cross 4 matrix space, maximally you can have 16 linearly independent matrices, and this is one particular set of linearly independent matrices. Okay. What is
Yes.
you can think of any other set of linearly independent matrices, any other independent set of 4 cross 4 linearly independent 16 matrices. Like, think of a matrix where every element is 0, only one element is 1. That is one matrix. And now think of such set of 16 matrices where one entry is 1, all other elements are 0. You can have 16 such matrices where 1, 1 is 1, in the other one, 1, 2 is 1, in the next matrix, 1, 3 is 1, others are 0, like that. So you can have 16. All these matrices are linearly independent. These are also 16 linearly independent matrices, a different set. This is, so there is a different basis. This is a different basis. But what is the beauty of this basis? What is the specification of this basis? Can you say? So suppose, look at this way. Suppose you have a set of 4 cross 4 matrices. So how many matrices does this set contains? How many 4 cross 4 matrices you have in infinite number of 4 cross 4 matrices you can have. Now, out of these infinite matrices, only 16 are linearly independent. Now you can choose this set of 16 linearly independent matrices in infinite number of ways. One obvious way is the way I just said, that 1 and others 0. In all these 16 entries, ones 1 and others zeros. So this set of 16 matrices are one set of linearly independent matrices. And you said that you have done in this class that this is also a set of linearly independent matrices. So what is so unique about this set? Can you tell me?
All includes gamma matrices. We can expand.
No, that is okay. That I can see from here, but that is not the. That is a
traceless Hermitian.
Yeah. All these matrices except one, all are traceless. That means, given any 4 cross 4 matrix, you can write it as a linear combination of 16 matrices. If you use this basis set, you can write any given 4 cross 4 matrix in terms as a linear superposition of all these matrices. Clear? That is the meaning of linear independence. But if you write it, the arbitrary matrix which you are writing as a linear combination of all these matrices, the whole trace of this matrix should be confined within the coefficient of the identity matrix in that expansion. Is it clear?
Yeah, right. Yeah.
So basically you are separating out any arbitrary matrix, you are separating out the trace part you are extracting the trace and dumping it as a coefficient in front of the identity matrix. Rest part is rest 15 matrices are traceless Hermitian matrices. Yeah? Not Hermitian, I mean, is it Hermitian? Here.
No, সবগুলো Hermitian নয়.
No, but traceless matrices, that's what I'm saying. Traceless matrices. Okay. So if I ask you this question, in 4 cross 4 matrix space, or in the set of 4 cross 4 matrices, how many traceless matrices you can find maximally which are linearly independent? What is the answer?
15 traceless.
15, because you can find 16 matrices which are linearly independent, but if you look at this particular basis set, then you can intuitively see that 15 matrices you can find which are traceless Hermitian, which are traceless. Here it may not be Hermitian. You can make this Hermitian by multiplying something by I or like that. You can do that. Choose these matrices because those are not Hermitian. You can multiply it by I and make it Hermitian by changing the coefficient. You can do that. But the thing is that for 4 cross 4 matrices, you can have 15 linearly independent traceless matrices. And truly, you can have 16 linearly independent, but you can choose a particular set where out of the 16, 15 will be traceless. In not all basis space, all the 16 will be traceless, but there exists a basis where 15 linearly independent bases are traceless. Clear? Is it clear?
Yes, sir.
Now, can you tell me if you have a set of 3 cross 3 matrices? Okay, 3 cross 3 matrices. How many of them? Say 3 cross 3 Hermitian matrices. How many of them are? So, how many matrices are? Or 3 cross 3? Sorry. Set of all 3 cross 3 matrices. How many of them are linearly independent?
9 matrices.
9 matrices. Now, can you tell me how many of them are in 3 cross 3 matrix space? How many matrices you can find which are linearly independent maximally and also trustless?
8 matrices.
Huh?
Identity বাদ দিয়ে বাকিগুলো
8 matrices. So in 3 cross 3 you have 8 matrices. In 4 cross 4 you have 15 matrices. In 2 cross 2, how many?
Pauli matrices, 3 matrices.
All the 3 Pauli. So in n cross n you have n square minus 1 number of trustless matrices, trustless Hermitian matrices, which are linearly independent. You can find. Clear? Clear?
Yes, sir.
So this is actually will be. I don't know whether you know this, or I will show you later that this is connected to this fact that there are 8 gluons for strong interaction. 3 quarks. 3 quarks makes a baryon. Here, since 3, so with this 3 there is some association of 3 cos 3 matrices, unitary matrices, and which means there are, in this space there exists 8 trustless Hermitian matrices which are linearly independent, and this existence of 3 trustless Hermitian 8 trustless Hermitian matrices corresponds to 8 gluons. That correspondence is the I will show you when we study H3.
এটা বলে ওটা কি গেলম্যান ম্যাট্রিক্স, ওটাকে কি গেলম্যান ম্যাট্রিক্স বলে?
3 cross 3 তে ওগুলোকে গেলম্যান ম্যাট্রিক্স বলে। Yeah, that 8 matrices are Gell-Mann matrices. যেগুলো 4 cross 4 এ তুমি এভাবে লিখছো, 2 cross 2 তে যেগুলো পাউলি ম্যাট্রিক্স, 3 cross 3 তে ওগুলোকে Gell-Mann matrix বলে ওই ফর্মটা। Okay, 2 cross 2 তে there are 3 matrices which are linear traceless Hermitian, তাই তো, n square minus 1. That is related to 3 gauge bosons W plus, W minus and Z, which are responsible for weak interaction. Gluons are for strong interactions, which is 3 cross 3. Weak interact, এগুলো জাস্ট আমি বলে যাচ্ছি, এগুলো কিছুই দেখাইনি, আমি জাস্ট weak interaction এর জন্য 3টে মেডিয়েটর আছে, W plus, W minus, Z. Strong interaction এর 8 mediators are there, 8 gluons. Electromagnetic interaction এর একটাই mediator, photon. Okay, so this one is U1, another is U2, another is U3. There are 3 kinds of matrix algebras going on. Okay, there, which we have to study to understand these beautiful interactions of particles. Okay, so in context of bolchi. Okay, but to show you this beauty of things, but okay, but here up to this point you don't need.
আমার ম্যাট্রিক্স গুলো আসছে এগুলো তো সেই লরেঞ্জ ইনভেরিয়েন্স এর জন্য আসছে, আই মিন লরেঞ্জ গ্রুপের ব্যাপার স্যাপার আসছে, তো ওখানেও কি রকম কোনো সিমেট্রি ব্যাপার আছে?
বুঝলাম না,
মানে এখানে এই যে জেনারেটর গুলো আমরা লিখেছিলাম সিগমা মিউ নিউ ওইভাবে, তো ওটা তো সেই মানে লরেঞ্জের গ্রুপের যে জেনারেটর গুলো সেই স্পিনার রিপ্রেজেন্টেশনে, তো আপনি যেটা বললেন এখন যে ওই গ্লুঅনের যে 8টা বা ওগুলো কি রকম কোনো সিমেট্রি কনসিডারেশন?
হ্যাঁ, সবগুলো সিমেট্রিক কনসিডারেশন আছেই, কিন্তু সেখানে লরেঞ্জ ট্রান্সফরমেশন নয়, সেখানে হয়তো অন্য ধরনের, সেখানে একটু অন্য ধরনের ট্রান্সফরমেশন। ওকে, সেগুলো আরো ইনভলভড। ওকে, সেগুলো কিন্তু আমি এইগুলো বলছি এই কারণে ইউ হ্যাভ টু আন্ডারস্ট্যান্ড দিস আন্ডারস্ট্যান্ড, মানে ইউ হ্যাভ টু বি উইথ দিস ডিরাক ম্যাট্রিসেস। Okay, this algebra of Dirac matrices should be at your tip of your pen. Okay, ওইখানে একদম প্রচন্ড সরগর হতে হবে. Okay. Now, okay, so the reason is I'm saying this is that these matrices are all 16 independent matrices. Clear? Now, have you studied Dirac bilinears?
Yes, sir.
And you know this. So these are 16 Dirac bilinears are these objects. Psi bar. So this, you put anything in, sandwich anything between psi bar and psi bar. So what you get? So this gamma R is any one element of these 16 matrices. So this is basically a 1 cross 1 single component object. Psi bar, gamma R psi. So R is 1 to 16 for each of these elements. So you have basically these objects. So when this is identity, you have psi bar psi. When this gamma R is gamma 5, you have psi bar gamma 5 psi. Okay, you have this kind of objects. Clear? There are 16 such objects. All are single component objects because of this 1 cross 4 into 4 cross 4 into 4 cross 1 thing. All these are single component objects. None of them are here are matrices. Clear? All of them are single component objects. There. From next class, so I think I will stop today because it's a good point to stop. Do you know how this quantities transform under Lorentz transformation? Have you done this?
Yes.
You know all this?
মানে আমরা এই লরেন্স ট্রান্সফরমেশন আর প্যারিটি ট্রান্সফরমেশনের জন্য কিভাবে চেঞ্জ হয় এগুলো করেছি।
ও, এগুলো করেছো? সবগুলোর জন্য করেছো?
হ্যাঁ।
Okay. So then okay, then I can show you the result. These calculations are there. Do you know this? I am showing you some result. Let's see whether you know this. Do you know this? Psi bar psi under Lorentz transformation transforms in this way. Under parity, it remains this way. Psi bar gamma 5 psi, Lorentz transformation change করে না, scalar. Under parity, it acquires a minus sign. এগুলো করেছো সবাই?
Yes, sir.
QFT ক্লাসে হয়েছে।
QFT class হয়েছে. Okay, then it is very good. This has been done. এগুলো এই নোটে তাহলে করা আছে, আমি তো জানি না তোমাদের হয়েছে, নোটে আমি করেছিলাম, নোটে তাহলে আমি আর বলছি না, আমি জাস্ট পরের দিন অন্য কিছু করাবো। So this is how all these objects transform. Okay, and you know this quantity transforms as a scalar under Lorentz transformation. Under parity, it does not flip sign. This quantity is also a scalar. Under parity, it's flip sign. That's why it is called a pseudo scalar. Okay, this name pseudo is for under parity. If it flips sign, it is called pseudo. Similarly, this quantity transforms as a vector under Lorentz transformation, and under parity, its space part does not change. Sorry, time part does not change. Space part flip sign. But when you have a gamma 5 with here, this quantity, the reverse thing happens. Time part flips sign, space part does not flip sign. So one is called a vector and another called is axial vector. You know this because for a vector, if x goes to minus x, a vector space part of the vector changes sign. Okay, that is a polar vector. But if vector does not change sign, it is an axial vector. Okay, so all these quantities, you know how they transform under Lorentz transformation and how they transform under parity. I have not written psi bar sigma mu nu this. Okay, now the reason we are interested in all this is because phi, these are the free fields, how they transform. These are the Dirac bilinears. Now free field, we have already seen this. Okay. By this, this. Okay. Clear? So
স্যার এটা একবার বলুন, বললেন বুঝতে পারবেন।
বললাম যে this is how these Dirac bilinears, okay, these objects transform under parity. There are 16 objects, কিছুটা কয়েকটা আমি লিখেছি, gamma mu, sigma mu, nu দিয়ে আমি লিখিনি। Now these are free Dirac fields, just summary of the previous result. How the free Dirac fields transform under parity, that we have already shown in today's class. Okay, free Klein-Gordon field, complex Klein-Gordon field, electromagnetic field কিভাবে ট্রান্সফর্ম করে, and Dirac field নিচে কিভাবে ট্রান্সফর্ম করে, এই দুটোকে ইউজ করে আমরা এগুলো পেয়েছি, তাই তো? Clear? It's just a summary of the previous results. What I am saying is that. Hello?
Hello, sir. You are not audible, I think, or my net connection is fluctuating. I can't understand.
You are not audible last few of seconds.
Hello? Okay. Now am I audible?
Yeah.
So what I am saying is that, so this is the, just a minute. So this is how the free fields transform under parity. This we discussed in this at the beginning of today's class, first part of the class. All these free fields like this way, plus minus, phase into this, mu transforms in this way, and psi under parity transforms in this way. Okay, these are the transformations of the free fields under parity and under Lorentz transformation also. Okay, these are scalars, this is a vector like this. This is a summary of this previous result. And also we have quoted here the field transformations of the bilinears, how they transform under Lorentz transformation and parity. Okay. Now if I ask you, construct a Lagrangian which is invariant under parity out of Dirac field and a scalar field. Out of psi and phi, write a Lagrangian involving these two fields. Just blindly I ask you to write a term in the Lagrangian involving these two fields, so that not just addition of free fields, just write one term involving both these fields as multiplication, such that the Lagrangian is invariant under parity. What you will do, you know how psi transforms under parity, you know how psi bar transforms under parity, you know how phi transforms under parity. Let's be a real scalar field, so either phi plus or minus. Okay. Now I ask you to write a term involving Dirac field and scalar field, such that term, that you write a function of these two fields such that this term is invariant under the transformation of space inversion. What you will write? Because that term has to be a part of a Lagrangian. Since that term has to be a part of a Lagrangian, the first thing is that the term in the Lagrangian should be a single component object. It can't be a matrix. Therefore, it should be either like, one thing you can think of, psi bar, psi phi into phi, for example, say. So this is one term constructed out of the free Dirac field and free Klein-Gordon field. And what is the property of this term? What that term physically represents, forget about that for the time being. But what is the mathematical nature of this term? Psi bar psi phi is a term which is a 1 cross 1 matrix. Okay, it's a single component object because psi bar psi is a single component. Now, this term does not transform under Lorentz transformation because psi bar psi does not transform under Lorentz transformation. Okay, Phi bar psi is invariant under Lorentz transformation, as well as phi being a scalar does not transform under Lorentz transformation. Clear? So this term is invariant under Lorentz transformation. Therefore, it can be a candidate for a Lagrangian, for a particular term in the Lagrangian. But it should not be a free Lagrangian because it involves product of fields. Okay, this we will see later. Now, what is the parity transformation of this term? You know, psi bar psi does not transform under parity. Now, phi, if it is a real scalar field, you see, it has to be real because if it is the Lagrangian in this form, Lagrangian is real, then phi has to be real. Phi cannot be complex. If I require phi to be complex, then the term should be phi star phi in the Lagrangian. Yeah. If phi has to be real, it can transform either as plus or minus. Now, suppose I want this Lagrangian to, this is not a free Lagrangian because it contains free fields, but as product of free fields. Therefore, if this has to represent some physical process, and if that physical process in nature comes out to be invariant under parity, then I can say then this field phi should select only the plus sign because this process is invariant under parity, should require under parity phi should transforms as a plus. If that process is the physical process whose Lagrangian I am writing like that, like this, if that Lagrangian has, that process is not symmetric under parity, if it violates parity, then this scalar field phi should transforms like phi goes to minus phi. Then only it can violate parity. So which of this transformation will be selected by phi is dictated by the actual physical phenomena, whether that physical phenomena is parity conserving or not. Okay. So this was the motivation for doing all these things. Now,
for a Lagrangian, যদি Lagrangian সেম থাকে, ধরুন L equals to L naught plus এই psi bar psi phi, এবার এই সেম Lagrangian কি দুটো থিওরি দিতে পারে, মানে একটা প্যারিটি কনজার্ভিং আর একটা প্যারিটি ভায়োলেটিং?
No. One particular so this is free Lagrangian plus some interaction Lagrangian. I am planning to construct this interaction Lagrangian. Now, for a particular, if you take a particular form of this, so first thing is that you have to first know at the beginning whether this interaction Lagrangian should be symmetric under parity or parity violating. Because the process whose interaction Lagrangian I am going to write, I have to know at the beginning whether that process which I observe in nature, whether that process is parity conserving or parity violating. If that is parity conserving, that tells me I have to construct the L-int in such a way that L-int is parity conserving, if that is parity conserving. Now, I want to construct a parity conserving Lagrangian out of Dirac field and phi field. Then there can be only one particular, there can be many combinations which can be parity conserving combinations. For example, this is a parity conserving combination where, okay, phi. This can also be a parity conserving combination, phi square, okay, phi cube. All are parity conserving combinations if phi goes to plus phi. Clear? For example, just one must suppose I want to construct a Lagrangian out of this Dirac field and a mu which conserves parity. Okay. Now, Lagrangian means there should not be any bare mu term there. Lagrangian is a scalar, so that mu has to be somehow contracted. Lorentz index has to be contracted, or two vectors should multiply, contracted to give you a scalar. And one obvious thing is this. This is a Lorentz vector. If you multiply it by a mu, this quantity is invariant under Lorentz transformation. This is a Lorentz scalar. Now, what is its parity transformation? This first part. What is the first part? The first part transforms in this way. Okay. Second, for mu I. Okay. And for mu equal to 0, it does not transform. For mu I, it flips sign. Now we want it to be parity conserving. If we want it to be parity conserving, then we know that this part transforms in this way. Then a mu, look at a mu. A mu can transform in two ways. Now, if this term has to be parity conserving, then a mu has to be like this only, because then only this negative term will cancel this negative term and whole thing will be parity conserving. Do you follow?
ওকে, তার মানে আমাকে এক্সপেরিমেন্টাল রেজাল্টই বলে দেবে আমি মানে কোন জিনিসটা নিয়ে কাজ করব, মানে a0 মাইনাসে না মাইনাস a0 a, তাই তো?
তোমাকে জগতই এক্সপেরিমেন্টাল রেজাল্টই বলে দেবে, আর বলে দেওয়ার কেউ নেই। তোমার তো বুদ্ধি নেই গোড়া থেকে কিছু একটা নেওয়া, এটা নিয়ে আমি কাজ করবো। যে কোনো থিওরি এক্সপেরিমেন্টাল রেজাল্টই বলে দেয় আমাকে কি নিয়ে কাজ করতে হবে। শুধু আমি প্রত্যেকটা ফিল্ড কি করে ট্রান্সফর্ম করে, প্রত্যেকটা ফিল্ড কি করে কাজ করে, জাস্ট একটা ফোন আসছে। হ্যালো হ্যালো, হ্যাঁ হ্যাঁ হ্যাঁ, ও সঞ্জয়, আচ্ছা ববি আছে? মোবাইলে অ্যাড কর, আমি মোবাইলে অ্যাড কর, আমি জাস্ট আমি ক্লাসটা শেষ করছি, আমি জাস্ট আমি 5 মিনিট পরে কর, 5 মিনিট পরে কর। ওকে, না রেস্ট নিতে হবে না, রেস্ট ঠিক আছে, রেস্ট নিতে হবে, 5 মিনিট পরে কর। ওকে, সরি একটা মিটিং আছে পরে সঞ্জয় আর ববির সাথে। এনিওয়ে, সো এইগুলো আমরা পরের দিন পড়বো, যে এক্সপেরিমেন্টাল রেজাল্ট ঠিক করে দেবে আমাকে একটা প্রসেসের কোন ফর্ম অফ ল্যাগ্রাঞ্জিয়ান আমি নেব। দ্যাট ইজ দি থিওরি। ওকে, সো হ্যাভ ইউ স্টাডিড চার্জ কনজুগেশন? হাউ দি ডিরাক হচ্ছে?
আমরা এটা করেছি ব্রেকের আগে।
ও, এটা করেছো, আচ্ছা। তাহলে এটা মানে তোমার যা করেছো তাহলে রিপিটেশন হলো আর কি।
না মানে ওই শেষের ব্যাপারগুলো অতটা ভালোভাবে অতটা এ করে দেখিনি আর কি।
তো ওকে, সো তো এই ক্লাসে যেটা করানো হলো, এই প্রত্যেকটা ফিল্ড কি করে, ফ্রি ফিল্ড কি করে ট্রান্সফর্ম করবে আন্ডার লরেন্স, সরি আন্ডার প্যারিটি, সেগুলো আমরা বার করেছি। এগুলো হাতে থাকলে ইউ ক্যান ইউজ দিস টু কনস্ট্রাক্ট ল্যাগ্রাঞ্জিয়ানস ফর ইন্টারঅ্যাক্টিং সিস্টেমস। ওকে, কারণ ইন্টারঅ্যাক্টিং সিস্টেমের ল্যাগ্রাঞ্জিয়ানটা কিরকম হবে এক্সপেরিমেন্ট আমাকে বলে দেবে, তার কি প্রপার্টি হবে, হাউ whether that will respect parity, I mean parity invariant or parity non-invariant, experiment আমাকে বলে দেবে। Now not only parity, there are also other aspects like whether that will be charge conjugation invariant, so whether C invariant or not সেটাও বলে দেবে, or whether C into P দুটো যখন একসাথে অ্যাক্ট করে, whether it is invariant under CP or not সেটাও আমাকে বলে দেবে। So for we have to, entering into that world. For that we have to, next class we have to learn how all these fields transform under charge conjugation. Charge conjugation means it is a transformation where you flip all the intrinsic quantum numbers of the system. Lepton number, charge, not only electric charge, all lepton numbers, all baryon numbers, strangeness, etc., etc., all the intrinsic quantum numbers that carries. If you flip that, now what it means in terms of that field, Okay, we will see that, because unless you enter into the quantization of fields, you will miss the connection between fields and particles. And that is it started? Has it? I think it is not started yet for your UFT class.
না স্যার এখনো হয়নি।
Okay, so but for the time being, just as the relativistic quantum fields, what do you mean by charge conjugation? You will see that. Okay, but you can appreciate that fully once you understand the quanta of these fields. I was thinking that in the, maybe I don't know when I can take the next class. When is my next class?
থার্সডে সঞ্জয় স্যার মেল করেছিলেন যে ওই দিন উনি ক্লাসটা নেবেন।
Oh, he told me to take the class on Saturday. Okay. Okay, let me see. So I was in a dilemma whether I should start charge conjugation at the beginning or I should give some elementary exposure to theory of quantum fields, because okay, so you tell okay, leave it, let me think. So next class I will think I will do this, how this charge conjugation takes you, I mean what does in terms of fields, flipping, changing charge of a particle, how does it been taken care in the context of fields, that we will discuss. And so we will discuss then how, if you, what is the meaning of this charge conjugation operator, because it is not some operation which you do in space time. Lorentz transformation is some operation which you do in space time. Parity is also some operation which you do in space time but discretely. Charge conjugation is also something which you don't do in space time. It is a transformation which is not related to space time transformation, which is, I don't think we have you done, can you recall any transformation you have done in physics which is not related to space time? Galilean transformation, Lorentz transformation, etc., etc. Can you remember anything where you are not changing the space time but you are calling it transformation? You have done it, but you have to remember, I mean, you have to click that you have done it.
ফেজ ট্রান্সফর্ম, কনস্ট্যান্ট ফেজ ট্রান্সফরমেশন, লরেন্স ট্রান্সফরমেশন নয় বা স্পেস টাইম ট্রান্সফরমেশন নয়,
Constant
ফেজ ট্রান্সফরমেশন ই টু দি পাওয়ার আই থিটা টাইপ,
to the power I theta type, or this electrodynamics gauge transformation করেছো না, যে mu x goes to mu x plus del mu theta,
মানে একটা স্পেস টাইম পয়েন্টে বসে
একটা
ট্রান্সফর্মটা
স্পেস
করছে।
টাইম পয়েন্টে বসে you are just changing the field.
Yes,
This
yes.
is not a space time transformation. This kind of
Yeah.
transformations are there. Okay.
Internal transformation type.
Internal transformation. So this is intrinsic transformation. So this is not related to space dynamics, space-time dynamics of transformation. So charge conjugation is a typical kind of that transformation, and you will see that for Dirac fields, it has its very beautiful, complicated structure. Okay, it is not true that simple things are always beautiful. Complicated things are also beautiful. There are more beauty in complicated things because it is the simplest things which takes the complicated forms. Okay. Anyway, okay, so let me stop here today. So I will send this because this calculation part, that where how each term translates, I explicitly have done this for you. I have not stated in this class. I have not discussed in this class. As you said, you have already done it, but the results are there. Okay. So thank you. Bye.
Okay.